Kelsey Young, incorporating field portable instruments into planetary surface exploration.
So hi everyone. First I'd like to say I'm really grateful to be speaking at this meeting, and especially in this session. I think it's a really important concept of incorporating geology into human spaceflight, and it's an issue that I think a lot of us in this room feel really strongly about. So I'm excited today to sort of conclude this session. We first heard from someone who's been there about the types of science investigations done on the lunar surface, and then I think Dave's and Jake's talks really showed you the breadth of activities that we have going on as a science, as a geology community, and working with the EDA and the human exploration community. That's something I think is really important. So today I wanted to focus on the area specifically talking about field portable instruments, so these higher resolution in situ analytical capabilities that we've been developing in the years since Apollo 17, and how we might think about building new instruments, building procedures and operations concepts for using them, and how we test those in relevant environments. So next slide, please. So field portable instruments, what do I mean when I say that? We want to maximize the science return of planetary surface missions without detracting too much from the operational capabilities of the folks who are actually going to be doing the exploration. So I see instruments as being useful in two different ways. You want to increase the in situ contextual awareness of the crew members doing the exploring, so tell them something more that they might not know without the instrument about the terrain that they're exploring. And there are also sample high grading capabilities, so deciding what samples we want to bring back for higher resolution laboratory analyses here on Earth. And I think portable instruments also have implications for analyzing fine-scale features that might be hard to collect and preserve for return to Earth, as well as potentially reaching hard-to-reach areas that might tell us something that we wouldn't be able to investigate without, as an astronaut in a spacesuit without the instrument. But I think those of us in this room who do a lot of field geology, there's operationally a lot different paradigm that we're talking about between just folks like Jack going out during Apollo and collecting samples, curating them, returning them to Earth, versus using these potentially time-consuming instruments that can be challenging operationally to deploy. So it's not as simple as just saying, oh yeah, throw a spectrometer on the mission, put it in an astronaut's hands, and they'll figure out how to use it. There's a lot of work that has to be done here on Earth prior to the launch of these instruments. And today I want to talk about some of the ongoing deployments that we're working on that searches to examine this problem. Next slide, please. So these are just a number of the ongoing field tests, both that have concluded and that are currently ongoing today, that help us to understand this problem of field portable instruments. So of course we had the Apollo surface missions up top. We learned a lot about conducting field science and other planetary surfaces, and those lessons learned, of course, still apply today. We actually have the Mars rover missions, which tell us something about which instruments work the best on other planetary surfaces and what suite of instruments can be combined to answer these compelling ongoing science questions. We have the Nemo mission, which I'll talk about, the NASA Extreme Environment Mission Operations, which is going on in Florida in an underwater habitat, which in the past couple years we've really tested the incorporation of these portable instruments, which I'll talk about. We had the Desert Rats missions, which you've heard about in the last couple talks. And then you have a whole host of other SMD and HEOMD funded field campaigns that look at a smaller scale about how these instruments work, and a number of them are of course funded by CERVI. Next slide, please. So we want to test in relevant environments. So we have a number of different field sites that many folks in this room are working in, and some of them that that I'll talk about today specifically focus on the utility of instruments in an analog environment. So we have the RISE CERVI team, which works at the December 1974 flow in Hawaii, as well as just recently the Kilbourne Hole and Petrillo volcanic feature in New Mexico. We have a PSTAR-funded Tovex project, which looks at the Lava Beds National Monument in California, which is looking at instruments that we could use to explore lava tubes. We have the NASA Nemo Project, and then we also have another PSTAR-funded project that's looking at the San Francisco volcanic field as a follow-up to the Desert Rats experiments that Dave Kring talked about earlier. Next slide, please. So I just want to talk, I'm going to run through sort of a shotgun approach of all the different things we're using to test these field portable instruments. On the smallest scale, we take a look at each individual instrument and what it specifically can tell us about the field geology of a site. So just really briefly to talk about the handheld XRF, over the last 6 years, we've actually calibrated this instrument to make sure that when we bring it out in the field, it's telling us something relevant. It's giving us good enough information to inform us about the geochemistry of the site. So over 6 years, we've calibrated with terrestrial terrestrial and lunar samples. We've looked at effects of sample roughness and sample preparation on data quality, and those results are published in that paper if you're interested. And so the point is here, for each instrument that you include in planetary surface exploration, you want to understand its limits and its advantages. And so the only way to do that is to calibrate it in the lab and then bring it out in the field and learn something about how you'd use it as an astronaut in future exploration. Next slide, please. So the Tovex project, like I mentioned, this is moving a little bit farther out. So once you identify, hey, this instrument could really tell you something valuable, you want to understand how it interacts with other instruments you might bring out, or collection technologies that you use to both collect, store, curate samples for return to Earth. So the Tovex project starts to get at that issue of what instruments make sense to use together in a relevant environment. So this environment specifically is dealing with lava tube environments, potentially you'd find on the lunar surface. So we're actually using GPR, LiDAR, seismics, magnetometry, and handheld XRF to explore a tube-rich environment. So we're actually exploring how these instruments interact, how they might be complementary or overlapping, and understanding what suite of instruments might make the most sense. So now that we've sort of talked about smaller campaigns where we test each instrument individually and how they might complement each other, we really realize that we need to test these instruments in a high operational fidelity type mission. The missions like Dave Crank talked about earlier with desert rats. So next slide, please. So desert rats. A number of us here in this room were involved over the course of the Desert Rats mission program. Like Dave Crank talked about earlier, this pressurized rover really enables the human explorers to get farther and farther away from landing sites and really increase the amount of science they're able to collect during a mission. We did incorporate instruments a little bit into the later Desert Rats missions. On the right picture, you see a habitat lab that simulates what the crew would be living in, and then dispatching rovers from that habitat lab to roam even farther and farther away from the landing site. So we actually had in situ instruments that we were able to use inside the laboratory to collect data during the course of that long duration mission. But we really weren't able to test the capabilities of an instrument actually used on EDA. So next slide, please. This is just showing the types of data that we're able to collect with, again, that same handheld XRF instrument I mentioned earlier. So the sort of colored plots on the right indicate data that we collected with the handheld XRF from samples collected by the 2010 Desert Rats crew specifically. And so what we found is that this in situ geochemistry data can really tell you something about the provenance of those samples and what the volcanic eruptive history is in a region. And specifically with Desert Rats, these instruments were deployed in the laboratory, and despite the fact that we're able to get even farther and farther away from the lab, it's harder to process that data real time while you're actually boots on the ground during EVA. While we go out terrestrially and we're able to differentiate between lava flows, it might be tough in the limited amount of time you have when you're boots on the ground. But having an instrument in the lab enables you to, on your downtime in the evening, process that data and understand, okay, I was actually looking at, in this case, 3 distinct flows here rather than just one. So we know that these types of instruments can really provide us with an enhanced contextual understanding of the geology of a region. But again, we want to really explore how these could be used when an astronaut's actually holding them in their hand rather than just taking that data in the evenings. Next slide, please. So the RISE survey team is aiming to get at how incorporating these instruments affects EDA timeline planning. So we know that it gives us increased science value added, but at what cost? At what hit to the timeline? And how much extra time do you need to allow for in your EDA planning to get that science value added? And is it even worth it? So that's what the RISE survey team is after with our field team. So basically you start with a science question. What are the valuable science questions you want to get out of a specific area? In this case, the December 1974 flow pictured here. Then you select your instruments. What suite of instruments even make sense? You evaluate the role of these instruments. What's the science value added? But then you also look at it from a human exploration perspective. What's the operational hit? And what are the recommendations for instrument development moving forward to account for this hit to your operational timeline? Next slide, please. So this is sort of our field structure that we use for the RISE project. We have a crew. We've experimented with crews of 3 people and crews of 2 people. And then we have instrument teams that deploy each relevant instrument when the crew asks them to deploy it. Next slide, please. So these are our 2 field sites for RISE. We work at the December 1974 flow at Kilauea on the Big Island of Hawaii. And then just recently, about a month ago, we got back from our first major deployment to Kilbourne Hole, New Mexico. Next slide, please. And here are some of the instruments that we've deployed with RISE. So we look at broad field of view and site context instruments, both from the ground with multi and hyperspectral imaging, as well as kite-based and UAV-based imaging platforms to give us that broad site context. And then we also use more in situ analytical capability instruments like the handled XRF, XRD, and LIBS. Next slide, please. So this is just some like hot off the press results from our field campaign. Like I said, we just got back, so these are pretty initial. But we did specifically 4 EVAs at the Kilbourne Hole site, and you can see the image on the right. There's the XRF in the foreground, and actually the LIBS in the background of the image. So we're deploying all of these instruments that I just mentioned real time with a crew in a relevant analog environment. And you can see some of the types of data that we're collecting and how these data sets start to mesh with each other. So it's really an iterative process, real time, to understand this might be redundant, or actually the hyperspectral imager in this case is telling us, hey, we might have missed something and we need to go back with the XRF and the LIBS data. Next slide, please. But what's the operational hit? The science value added is important, but what's the cost? Next slide, please. So in this specific case, I won't go through the details, but essentially if you have an EVA of approximately an hour, each individual XRF measurement specifically takes about 2 minutes. It's a 2-minute operational hit to get that in situ geochemical information. But if you look at the XRD data, that can actually take up to several hours to acquire. So while that data might be really important and really exciting scientifically, is it worth the 3 hours? So what we were finding was our crews at RISE were actually using one instrument to high grade for the next. So if they identify a really diverse suite of samples with the XRF, which has a low operational cost, they could then feed forward the most compelling samples into the XRD itself. And we were really intrigued by this. They sort of came up with this naturally. So we actually sought to expand to other analog projects to sort of see, to develop that a little bit more. Next slide, please. So with that comes the Nemo Project. So the Nemo Project, we just finished Nemo 22 a couple weeks ago down in Florida. So this is a really high fidelity integrated analog mission in a really extreme environment, right? The crew's living 60 feet underwater. The science and science operations are analogous to planetary surface exploration, and specifically in the last 2 missions, we've worked on incorporating relevant instruments. And while they're not XRF and XRD, of course, because you're underwater, it's very comparable. We had one instrument that took just a couple minutes to acquire and one instrument that took much, much longer. So we were exploring the relationship between short duration and long duration instruments, like what we identified with RISE as being a potential operational concern. Next slide, please. So we implemented this sort of instrument high grading and exploring in a high fidelity environment how these instruments might play off of each other in this sort of integrated scientific environment. So we actually had a science backroom over different varying communication latencies. We had an IV, an intravehicular crew member who could sort of quarterback the EVA, and we had 2 EV crew members who were working on collecting samples and using these instruments. So we're actually incorporating real-time during an EVA inputs from the science team based on instrument data that was coming back. So based on that instrument data, we were informing as a science team the crew of what samples we wanted them to collect and curate. And in this environment specifically, the threat was very real because sampling, permitting is very limited in this environment. So we were really using those instruments to make sure that we're collecting the most scientifically robust samples possible. And in fact, Nemo 22, the picture on the bottom right, we were actually deploying 2 of these long duration instruments simultaneously to understand how the crew might switch back and forth between using these long operational hit instruments. Next slide. And what we ended up finding was that, especially with these more complex instruments, there's just a lot going on for the crew to have to manage. So we wanted to give them a data product to help them run through procedures, to keep track of the data and say, hey, this kind of looks like something we saw 4 days ago. Let me actually pull up the data and be able to see that real time. So out of that came the Nemo developed electronic cue cards that they were actually able to look at on an underwater iPad. So everything, it's hyperlinked, so you can click, every button is live, and you actually click and you can see data from previous days and look at procedures and stuff like you see here. Next slide, please. So we found at Nemo that these cue cards were really beneficial. The crew liked them a lot. They were able to interact with them, able to view data. So we implemented them this year for the 2017 RISE campaign. And so we actually see similar cue cards here where you're able to interact with data collected on previous days, look at your traverse plan, look at the initial science objectives for your site. And you can see some of the results here across the bottom. We have the XRF and LIBS data collected from a previous EVA as well as some of the hyperspectral data. So both Nemo and RISE really demonstrated the utility of these daily iterations on these data products to help review data products from these high-resolution instruments to refresh your memory and not have to keep track of a million things at once. Next slide, please. So the next generation, really quickly, my last slide. is the Shire Project, which is a newly funded P-STAR project that's meant to incorporate multiple instrument data streams in a virtual reality environment. Because the thing that we're really missing here is developing these operational protocols, which can be quite complex. And what we want to do is, field work is critical, right? We have to go out in the field, we have to put these things in a stressing environment. But what we can't do in the field as easily is rapidly iterate on procedures in a repeatable testing environment. So by incorporating this high-fidelity scientific data from the field into a hybrid reality environment, we're able to test the procedures in this repeatable way. So this is a new project based on some RISE survey data that we're going to be implementing soon, and we're excited about being able to understand what this new relevant environment can tell us about instruments. Next slide, and I'll leave it up. So conclusions, portable instruments are really exciting. There's a huge capability to give us science value added, both as terrestrial field geologists and as planetary surface explorers. But there's a lot left to do to understand the operational capabilities and constraints of these things. And what we need to do is continue these really wide variety of integrated testing campaigns to understand the strengths and disadvantages of field portable instruments. Thanks. So if we could get all the speakers back up here, we'll have you come up for the panel discussion.
You want to work your way up, and you can have a seat over here. I'll sit over